All right, here we are back at it again with the Roller Coaster Connects kits. We're using the same ramp as we did for the Speed Lab, but this time we're looking at acceleration. And instead of measuring the entire distance each time, we're going to do segments that get longer each time we take a measurement. Our first measurement, to give us enough time to get an accurate measurement, is going to be at 4 track segments. Now, track segment is nice. It's actually exactly 20 centimeters. So 4 of these track segments are going to be 80 centimeters, and then we're going to add 2 each time, at 40 centimeters each time. And we're going to take a measurement of how long it takes the car to go that distance. Since we're using our photo gates, and that's a super accurate way of measuring the time, we're not going to have to take an average. So if you're following along with the video, you only have to record one number in your chart. And that number is what we will graph later. Okay? You've noticed that I've offset these just a hair, and they're offset by the same amount. So the distance that we're recording is actually the 40 centimeters, or I'm sorry, 80 centimeters that we need. Okay? So let's get our first measurement. We've set the photo gates up. Here we go. All right, that was quick. 0.89 for just those 4 track segments. Let's go ahead and round it to the nearest 2 decimal places, which makes it 0.90. All right, we're going to reset the photo gate, move it down 2 track segments. So we need to lower it to make sure the cart goes through it. It's really nice. The cart fit perfectly through these photo gates. All right, reset the timer. Okay, now we're doing 120 centimeters, 6 track segments. Right? 1, 2, 3, 4, 5, 6. Yes. All right, 6 track segments. All right, 6 track segments. All right, 1.25. Okay, now we're going to do 8. This to work. All right, we're set up for 8 track segments now. All right, now we're ready for 8 track segments, 160 centimeters. Oh no, that doesn't work. We'll have to do that one again. Sometimes it's tricky, it just barely fits. All right. Now we're ready for 8 track segments. This is 160 centimeters total. There we are. 1.59. Let's round that to 1.60. All right, and last but not least, we'll have the whole 2 meters. 200 centimeters. right, we're set up and ready to go for the full 2-meter section, 200 centimeters. Ready? Good. 1.84. All right, so now we've got our measurements, our times for each amount of track segment. We've added 40 centimeters every time. And of course, as we added distance, our time increased, which was to be expected. Now that we have all the times for each track segment, we need to figure out the speed at which the cart covered those track segments. Now remember from our last lab that speed is distance over time. So we're going to take our times and our distances and divide the distance by the time it took to get there. So let's go ahead and calculate that for each of our measurements. 80 divided by 0.9 is 88.888. Let's go ahead and round that to 88.9. That's meters per second in our units for our speed. We'll do 120 divided by 1.25. 96. Let me correct that. It's not meters per second. We did centimeters, didn't we? Centimeters per second. So that's what our distance was, not meters. 160 divided by 1.6. Should have been able to do that without a calculator, shouldn't I? 100. And 200 divided by 1.84. 108.7. All right, so how did the speed change as we lengthened the track and let it go down more of the ramp? Remember, the height of the ramp stayed the same. So what was changing was it was gaining speed as it rolled down the ramp. So our speed increased as it went down the ramp. So what we're going to do next is graph this data on a distance time graph, and then graph it again on a speed time graph. See how those numbers look. Okay. All right, so our seconds here, 2 seconds is our longest time. We could have stretched it out more, but that's okay. 1.84 and 200 is our last point. Let's do our first point. 80 and 0.9. Our second point, 120. Okay, so we're going up by 20. We've got an increasing speed each time, increasing time. So, is the slope of our line constant? It's changing. Okay, our slope should be getting steeper each time. So our slope of our line, now that we've got this graphed, is getting steeper as it gets faster. Okay, so we know that the slope of a distance time graph equals speed. So it gets faster and the slope gets higher. A changing slope on a distance time graph indicates an acceleration. It's getting faster. It's changing speed. Okay? Let's graph our same data on the speed time graph. So at 0.9 seconds, we had a speed of 88.9. That's almost 90, so we'll put it right in between. Okay, our first point is 88.9 and 0.9 seconds. So that's almost 90 and that's almost 1. Okay. Next point is seconds, 1.25 by 96. speed. So 1.25 by 96 and 1.6, 100. Okay? Our acceleration is change in speed over time. How fast do you go? How fast can you get to a certain speed? Okay? We often denote acceleration for cars in 0 to 60 in 8 seconds. Okay? Well, it's a change in speed over time. So this time when we do our slope of this line, our change in y over change in x, we do a change in speed over a change in time. Okay? So if we were to write out that formula for the slope of this line, the change in y over the change in x, that's like saying the change in speed over the change in time. And that's what acceleration is. Acceleration is the change in speed. How fast can you change your speed? 0 to 60 in so many seconds. And when we do our value for acceleration, we have centimeters per second, centimeters per second, That's our unit. Speed over time. Now, you'll see this sometimes written as centimeters per second squared, because the time and the speed have seconds in them. We can combine it